Okay, so let me start by wishing Mustansir and Deepak many more healthy and productive years ahead. They have been a great inspiration to the statistical physics community in India and abroad. Now, before I start my scientific part of my talk, I would just like to say a few words for just about 2 minutes about Deepak, as I might not get the opportunity later. So as some of you may know, that Deepak was my PhD advisor. Working with him was a great academic adventure, full of inspiring challenges and many exciting discussions. As an advisor, he not only shaped and nourished my academic personality, but he was and still is an inspiring role model. However, it is not only his academic excellence, but his personality, his ethics in everyday life that was awe-inspiring for me. I want to share one tiny story out of many precious experiences I had, which reflects his personality and in fact influenced my perspective in life. So when I started my PhD, there was a tiny sketch of pattern, something like a doodle on the left corner of his whiteboard. So particularly those of you who had discussions with Deepak in his office in TIFR may remember that sketch on the whiteboard, as he was very careful to preserve it. The artist behind the sketch was Deepak's daughter, Prachi, when she was just a kid. The sketch remained untouched on the whiteboard for decades until Deepak retired and I took over his office. Being aware of how Deepak cherished that small sketch, I wondered if there is a way to preserve it for him. On the very last day, just before he was leaving his office, I proposed that I will do something about it. He declined and went to the whiteboard and simply erased it in one swift move. In my personal life, I know how hard it is to cherish and preserve small things, but even harder it is to let it go when time comes. Some such small yet deeply meaningful actions, that is the defining personality of Deepak to me. So, all right, so let me tell you now the scientific part, which will also be a bit short, hopefully. Okay, so this work that I'm going to present to you is done primarily with Bernard Derrida and Ori Hirschberg. So let me first give you the bare bone result. Okay, so it is about a class of diffusive transport models with a single macroscopic conserved quantity. The circles could be particles, energy quanta, or electric charges, etc. The system is connected with two reservoirs at the two ends, and they could be of different densities at different temperatures or voltages. Now, after quite some time, the system settles into a non-equilibrium stationary state with a non-zero flux. So our results are about the macroscopic characterization of that non-equilibrium stationary state in a coarse-grained scale, as shown in this kind of sketch. Okay, so now, particularly the result is about that we give probability of fluctuations of macroscopic density in the large system size limit, and it has this following asymptotics. This is something similar to that Landau description and equilibrium. The second result is about the probability of flux over a large time t, and it also has a very similar asymptotics. Now, of course, there have been many earlier seminal results, particularly by the group of Derrida, Lebowitz, and Bertini, and many others. So what is new about our work is that we extend those earlier work by including the effect of coupling to the boundary reservoirs. And that I will just explain what I mean by that. And our results are about expression of these probability functions, the exact expressions, for the class of model systems whose microscopic dynamics are either Bethe integrable or Bethe non-integrable. Okay. So now, why is this question relevant for us, and why did we start looking at this question? Now, a motivation for us came from a simple outlook, and that was that how to generalize the StatMech outside equilibrium, what many people have been working on. Now, very simply, that in equilibrium, when a system is coupled with a single bath, probability of a density or magnetization profile is given by this Landau kind of free energy functional, okay? And the free energy functional comes from statistical mechanics. The function is a state function for one reason, that it is insensitive to the precise coupling of how you couple to the system to the reservoir, okay? Now consider the very similar things outside equilibrium, okay? And for example, now you take the system coupled with two different reservoirs. Now we don't have those Gibbs-Boltzmann distribution and Landau kind of form, but there is this large deviation theory which tells that for some system, it is possible to write in a similar exponential form, okay? And F is what is proposed as often as the analogous to the Landau free energy. Now the question is, can the F function here outside equilibrium in a non-equilibrium stationary state, can it be robust against the coupling of the system to the boundary? And in some sense, can it be a state function? Okay. Now this is non-trivial considering the long-range correlation that usually are present in outside equilibrium systems. Okay. All right. So the question that I want to discuss in this talk is how robust are the non-equilibrium fluctuations, particularly that free energy function, quote unquote, to the coupling with the boundary reservoir. Now to address this, we started addressing this question by going back to the very well-known tractable models of non-equilibrium system, and that is the symmetric exclusion process. Now to take care of the boundary coupling with the system to the reservoir, we varied the time scale of how the system couples to that of reservoir. So what we do that we take the rates and make them of the order of 1 over L to the power alpha, where L is the system size. So if alpha is large, then the system, then the boundary rates gets very small in the large system size limit, and the system gets almost like an isolated in a time scale. If alpha is 0, then the boundary rates are of similar order as that in the bulk. Another question that we ask in an exact solution, that how robust are these non-equilibrium fluctuation or bulk fluctuations as a function of this alpha. Okay, so now in equilibrium, we know that this change of boundary rate would not affect the bulk fluctuations. However, outside equilibrium, they matter because the dynamics is important. So now this model, although we don't have a starting Boltzmann-Gibbs distribution, but this model is tractable and has been solved microscopic. Its microscopic measure is known. So now what is the result? So the result, you can see it in this kind of following sketch, that as a function of now the alpha, you'll find that alpha equal to 1 is a marginal point. So if you take alpha less than 1, where now the boundary rates are of similar order to that of the bulk, then there is a single free energy function which describes the macroscopic fluctuation or the non-equilibrium stationary state. If you go alpha above 1, then it is the statistics are described by a single free energy function, and that is that of an equilibrium distribution. So this is more or less just the result that come out of the analysis. These results come out of an exact solution. So for this particular system, and you can write down, for example, for the density fluctuation, that particular F function, which are usually known as the large deviation functions. The same thing you can, so I will not talk about much about this particular function. I just flashed it just to show you that you can get the exact expression for this free energy functions. Now, the same thing you can also say for the current as well. And there is a similar exact expression, but the qualitative feature remains the same. Okay. Now, how did we solve it? It requires some methods of integrability, but that I don't get into. Now, the question is about, so how general is this observation that we see that there is a robust fluctuation in the non-equilibrium stationary state? Now, I first give you one example, and it's quite, there is this very famous paper by Lee, Levitov, and Yakovet, and well-known, that where they studied transport of electron in a disordered conductor in the short noise limit. And surprisingly, it is found that if you look at the current statistics, the F function is exactly the same as in the strong coupling limit of the exclusion process. Now, is this surprising? Possibly not. And this is what relates to earlier works of Deepak and Mustansir. They explored this aspect that how symmetric exclusion has a one-to-one mapping with that of a Heisenberg spin chain. And in this way, you can think of that the results may not be that surprising, this coincidence. But how about other systems where such mappings do not exist? So in order to understand that, in general, you have to go through a more general approach, which is the fluctuating hydrodynamics. For such system, this has been already studied quite a lot, and this is known as this macroscopic fluctuation theory, a la Jonah-Lacinio et al. Now, roughly the idea is that you, rather than looking at a microscopic dynamics, you look at the evolution of the conserved field, and you look at the evolution in time, and describe probability of each such histories using an action, so exponential of an action. Okay. Non-triviality are often is how do you find that action? And there are many different ways to do that. So just to give you an example, that for the example of symmetric exclusion process that I showed, the action looks something like this, that there is a bulk part, it has a Lagrangian structure, it has a bulk part, which is in blue color, and then there
you
are
have
the
2 more
boundary
minutes.
terms. Yes, thanks. And so you have the 2 boundary terms. But the point is that once you do this hydrodynamic field theory and do the minimal action path, the standard procedures, then it actually reproduces the answer that we got through this microscopic solution, including that the effect of the boundary. So that is something the new result. Now, what is this then hydrodynamic theory is good for? That it is the generality. And it tries to answer then the question of how general are these qualitative behavior that I talked about. So I just give you one example. So if you just take the same symmetric exclusion process, but now make the exclusion, not just one particle exclusion, but you allow in same site, let's say n number of particles, but it cannot be have more than n particles. In that case, you can also similar way show that there is a mapping to a quantum spin chain, but now it's a n cross n representation of that SU2 group. Now the point is that if you look at this microscopic dynamics, then it is Bethe non-integrable. But if you look at this hydrodynamic description, it is integrable. And you can solve the problem and get the same, very similar qualitative result. And you get those large deviation function that I mentioned. The one more example that you can, if you look at, there is a famous model of heat transport. It's called Kipnis-Markiorov-Presutti model. Its microscopic dynamics also has a mapping to a non-integrable SE11 spin chain. So the microscopic dynamics is difficult to solve, but the problem could be solved in that hydrodynamic way, including that of the boundary within the hydrodynamic approach. So at the very end, what I wanted to say, the take-home message, is that for the class of diffusive system that we analyzed, you can see that the macroscopic fluctuations has certain amount of robustness with respect to the coupling to that of the boundary. Okay, and in that sense, you can think of it as like a state function. The second point is also quite interesting for me, is that there is some sense of universality in the following sense, that your microscopic dynamics of different models could be integrable or non-integrable, but their macroscopic descriptions could be solvable, okay? And they could give rise to a very similar qualitative behavior. So with that, I thank you for your attention.
Thank you, Tridib, for a beautiful talk and also a beautiful story. And the session is now open for questions.
Sorry, I have a question. Tridib, I'm just wondering if your particles, let's say, were hopping unidirectionally, or if they were active Brownian, those kinds of things, do you know what would happen? Because in those cases, you know, the boundaries matter a lot for many purposes.
Right. So in the case when there is a, like, for example, ASEP or TASEP, so there this diffusive hydrodynamic theory that I explained is hard to define to all levels of fluctuations or all correlations. So that is part is still, I believe, is still to be explored.
Okay, thanks. Anyway, beautiful talk. Thank you.
So, okay, there are 2 more raised hands, Abhishek Thar and Rahul.
I wanted to ask, sorry, Abhishek first.
Go ahead, Deepak.
Yes, Deepak.
Abhishek first.
Okay, I'll ask. Yeah. So, I mean, this. So there are some models like this harmonic chain with stochastic noise,
Right.
For some of which I think like if you have momentum conservation, then you have anomalous transport and so on. But there are some exact results in those cases. But now from this MFT, is there anything that one can say from this kind of like trying to construct a free energy?
So this is the thing. What I found is in those direction also something that Sriram asked. I found the work of Sasamoto, recent work of Sasamoto, is very interesting. It seems like there are certain systems, even on those driven bias direction, you can generalize MFT and actually get back those exact microscopic results. But this definitely needs to be explored more.
Okay. Okay. Yeah. Okay, thanks.
Deepak?
Yes. So I had a question. You said that there is this boundary alpha equal to 1, which separates these two qualitative regions. Why is the boundary at alpha equal to 1?
So intuitively, the way you can understand that, see, alpha equal to 1 means the boundary rates are 1 over L. And it turns out in these diffusive systems, your current is of the order of 1 over L. So the information, I mean, it's not even a hand-waving argument, but I feel that the information that it propagates by that current, which is order 1 over L, has something to do similarly with the alpha equal to 1. But it is not even a hand-waving argument. Yes.
Okay.
Rahul?
So yeah, my question is basically in these regimes where you vary alpha. So one is where you have an equilibrium, and one you have where you have non-equilibrium. So does MFT handle all values of alpha? Is there
Exactly. MFT handles all values of alpha. So that's a bit of non-trivial part of the calculation came, that it was a bit tricky to include the boundary effects where there is no local equilibrium. Okay, and that's why that applying MFT to get these boundary effects was a bit tricky, and you needed to do it a bit carefully and to construct the MFT to get those results correctly. Because at the boundary, when you change the very different alphas, this local equilibrium thing is not valid anymore, just across the one bond that connects the system with the reservoir.
Right.
So it gets a bit tricky. That's what I wanted to say. If you want to do really the MFT and get back this result exactly.
Okay, thanks.
Okay, so we have a general comment from Fazil Najib in the chat box. Not a question, but a compliment. It was an amazing talk. Yeah.
Thank you.
Okay, thanks. Thanks, Tridib, and let's...
Just